Review of a 32-foot Mirage Center console. I performed my project in the field of naval architecture and marine engineering at Donald L. Blunt and Associates, which is a design firm in Chesapeake, Virginia. Personally, this is the career that I wish to pursue. I'm going to school to get a degree in naval architecture and marine engineering. And this career path better suits my interest than any other career I can find. I have salt water flowing through my veins. I live at the beach, I surf, I fish. And I needed to find a career where I can stay. Locally, we have a very strong recreational industry. Lots of average Joes out there have their 18 to 22-foot boats that they like to take out and cruise around on the weekends. So they go out, they buy fuel, they buy fishing bait, and they support our local economy. But we also have the Navy here, which is even more significant to our local economy. And every Navy vessel that exists, not only here, but in the entire world, was designed by a naval architect and marine engineer. But globally, every piece of clothing, or just about every piece of clothing in this room, is labeled made in China. And every piece of clothing was brought over here from China on a container ship because travel by sea is still the cheapest and most efficient way to move large quantities of materials. So in my project, I analyzed a vessel that I work on. I work as a fishing mate on the RRB, and it is a 32-foot Mirage Center console. A little bit of background is the engine is 310 horsepower, and we've put 1,800 hours on that engine in the last 3 years. So that means that we use this boat a lot. So any minor change that I could make to improve the efficiency could have drastic impacts on the cost effectiveness of this vessel. It's propelled by a Volvo Penta duo prop stern drive, which I'll discuss a little bit later, and it cruises at approximately 22 knots. A knot is 1 1/8 mile an hour, so that's approximately 25 miles per hour. So when I started this project, I wanted to know, is the RRB performing at its optimum potential? To answer this, I had to ask, how fast should she go? How much power should she need to go that fast? How efficient should she be at each of those speeds? And then how does she compare? So unfortunately, I had to go out on the boat one day and run it around in circles to figure out how fast it goes, in the sun, and it was miserable. So basically the final question was, is there a way to make the RRB perform better? To start this, I had to create a model of the hull form. To do this, I created a table of offsets where the boat was put on dry dock, and I measured the height of various hull structures from the ground. This is the keel, which is the bottommost line on the vessel, the chine, and the shear. And I measured the heights of each of those off the ground and input those into AutoCAD to create the stations drawing as shown here. After I created that model, I measured the location of the static water line, which is where the water sits on the vessel when it's not in motion. From this, when I plugged that information into a computer program called GHS, or General Hydrostatics, which told me the weight of the vessel and the location of the center of gravity, which are both important to future predictions. I had to ensure that all these measurements were done at full load condition, which is when all the maximum amount of material that's ever going to be on the boat is there. So we're full of fuel, full of fresh water, all fishing tackles on board, all the people are on board. And then I could run predictions at a constant condition. So after I verified that condition, I ran resistance predictions. On a boat, there are two major kinds of resistance. There's the bare hull resistance, which is the resistance due just to the hull form that was shown in the model before, and then appendage resistance, which is anything else that is interacting with the moving water. To calculate the bare hull resistance, I used the Savitsky semi-empirical method. What Savitsky did to develop equations was he analyzed a planing hull, which is or a prismatic hull, which is where on a normal boat you've got nice curves. He used straight lines. Everything on his vessels was straight lines, which significantly simplifies the math. It removes calculus from any kind of geometry. And then I compared my calculations from the Savitsky method to a standard calculation template that was developed by DOBA, which was a slight improvement on the Savitsky method. Then I looked at the appendages. The only major appendage on this vessel is the Volvo Penta duo prop stern drive shown here. So this vessel, everything below this line interacts with the moving water. So you can't see very well, but there are 3 sections of this, or I broke this outdrive up into 3 sections to calculate the resistance. The airplane wing, which is just a vertical airplane wing, the torpedo, which is where the shaft is housed, and then there's a skeg down here, which is just a very thin plate that extends down to improve stability. I used fluid mechanics literature to calculate the resistance of both the torpedo and the airplane wing, and the Savitsky method to calculate the resistance of the skeg. After I knew the resistance of the vessel at various speeds, I was able to predict the performance at different speeds. So I was able to predict how much power was needed to achieve any given speed. To do this, I used the small craft power prediction, which is a paper by Blunt and Fox. You'll notice Blunt is the same name that's on the company. He's the same man who founded the company that I work for. So when you're looking at speed and resistance prediction, and your power required, your main variables that affect this are the resistance of the hull at that speed, and then also the engine. Different mechanical contacts can cause losses of efficiency and power. So the mechanical arrangement of the engine to the propellers can change the amount of power the engine needs to produce to achieve the same speed. I then looked at trim tabs, which are plates mounted to the back of the vessel, as shown here, and can be inclined into the moving water through a hydraulic pump. When these trim tabs are deployed, it creates a trimming moment, which is when the boat rides, it sits like this up at an angle. But this trimming moment can pull the bow down and reduce that angle, which if the angle is reduced enough, can decrease the resistance of the bare hull. While if the angle is not decreased enough or is decreased too much, the resistance will increase. So I had to calculate where that ideal trim was at speed, and then calculate whether the trim tabs would do the job there. I again used the Blunt-Fox article to predict the performance of the trim tabs, and concluded that they were not large enough to achieve minimum trim or minimum resistance. After I made these conclusions, I went out and I had to do sea trials. In a sea trial, I again had to ensure a full load condition because that's where I perform my predictions. I had to select a calm day because waves or wind affect the resistance of the boat and can change the performance, which can give false results. So during the sea trial, you set the engine at a specific RPM. Let's see. I think I started at 500 RPM, 1500, 2000, 2200, etc. And measured the speed, trim, and fuel consumption at each RPM in a specific direction. I then turned the boat 180 degrees and did the same thing again. By turning the boat in the opposite direction, you theoretically account for any wind resistance or wave resistance, and by averaging those two values, you essentially create a net external impact of 0. I then manipulated the trim tabs and repeated this procedure to measure the change in performance with the use of trim tabs. I only used trim tabs at full deployment, which is approximately 15 degrees into the water, or their maximum possible effect. So this is a graph of power versus speed in knots, the power produced. The red line is my predicted power produced at speed, and the yellow points are my measured points at speed. You'll notice from this graph that the yellow points match very closely to the red line, and within my margin of error, I concluded that the vessel was performing at its proper potential, and there was nothing that could mechanically be improved to improve the performance. I then looked at the efficiency of the vessel. There are two things in the efficiency you could tell me. Well, I looked at the efficiency of the trim tabs first, but also I looked at where the most efficient speed was. Because if we change, even a small change in efficiency when you're using the boat as much as we do, will change the cost of running the vessel. So I looked, and obviously the most efficient point is up here at 6 knots. Well, 6 knots is way too slow for our uses. We like to get where we're going so we can go fishing. So I had to move to the upper end of my register, which is between 20 and 28 knots. And you'll notice that the optimum potential is about 22 knots, which is where we already ran the boat. So again, I could not make the recommendation there, which could improve the efficiency. So when I looked at the trim tabs, which are the yellow points, I noticed that at 18 knots, the trim tab slightly improved the efficiency of the vessel, but at 24 knots, the trim tabs the efficiency slightly decreased. But I maintained my conclusion here that the trim tabs were too small, and I needed a new system. What I came up with was the use of Humphrey interceptors. A Humphrey interceptor is seen down here on the bottom, which is this black plate. As opposed to a trim tab, which inclines into the water plane, the interceptor inserts a plate perpendicular to the moving water. So instead of changing the angle of incline of the trim tab to change the trim, you increase the area of the plate that's interacting with the moving water to change the trim. What this does is it reduces the appendage resistance of the trim tab, the appendage resistance of an interceptor is less than the appendage resistance of the trim tab, which increases the efficiency slightly, but they also perform better and at a wider range. So it's much easier to adjust the trim and therefore improve the efficiency. What's really cool about this system is it has active ride control. The active ride control system puts an accelerometer inside the vessel. So when you're running along, you're usually rocking and rolling along. But this accelerometer measures your pitch and your roll and uses these interceptors to counter that. So you run on a much smoother course, which puts less stress on the engine and less stress on your tackle, again saving you money. On a preliminary, I haven't had a chance to do an official sea trial, but on a preliminary sea trial, I've found that the interceptors have increased the efficiency of the vessel by 20%. So my final product in this work was a technical paper written for the owners of the vessel and a technical presentation to the owner of the vessel. On feedback from my mentor, I received 3s and 4s for my work experience, which you haven't met him, but if you did, you would know that he's the most difficult person in the world to please. So that is, I'm very pleased with a 3 and a 4 from him. If you look at my presentation, you'll notice that my lowest score was on professionalism, which was a 3 on the 5-to-1 scale. This was because I got comfortable with my knowledge of the technical content, and I was comfortable with with the client and everyone that was in the room during my presentation. So I relaxed and the presentation became much too casual. I'd like to thank my mentor, Mr. Jeffrey Bowles, the Bowles family for allowing me to use their vessel on this analysis, my family for supporting me in this endeavor, and then Ms. Graves, because I think that I gave her more work than she gave me, so I may or may not have been irritating her. I'll be in the back corner over there if you have any questions later. Thank you.